We are giving examples of fields of the form fx mod ideal generated by a polynomial little f, where little f is a irreducible polynomial in capital Fx. Like there's example 2 and example 1 here. In both these cases, the fields that you got were fields that you could actually recognize. In this case, it was C. In this case, it was Q add square root 2. We say call this field Q adjoint square root of 2. So it's a subfield of real numbers. So in example 3, we'll see something which is truly new. So this will be a field with, we'll construct a field which has 8 elements. 8 elements. A field with 8 elements. So we'll start with the field with 2 elements, F2. Okay, so remember F2 just means Z mod 2. So just 0 and 1. And rather than writing 0 plus 2 and 1 plus 2, we'll just write 0 and 1. Okay, otherwise notation will get too confusing. So we take f2x, and in f2x we consider the polynomial be the polynomial x cubed plus x plus 1. Now first claim that this is irreducible. And so note f of 0 is 0 plus 0 plus 1, 1, and f of 1 is 1 plus 1 plus 1, 3, which is also 1 in Z mod 2. So both these are non-zero. And then a cubic equation, if it factors, then it will have a degree 1 and a degree 2 factor. But if it has a degree 1 factor, then it would have a root in F2, but it doesn't. So this implies this argument we have done before. Fx is irreducible in F2x. So if you take f2x mod the ideal generated by this polynomial, this is actually a field. That's our theorem. A polynomial is irreducible in f2x means that the ideal that it generates is a maximal ideal, which implies that this quotient is actually a field. And in fact, we also saw that we naturally identify f2 inside here by sending an element of f2 to the corresponding coset. Now, what are the elements of this field? The elements of this field, where do we write? Maybe we'll continue here for a little more. The elements of this field are given by polynomials of degree up to 2. So what I'm quotienting by is a degree 3 thing. And this lemma that we did, which we have been using, says that when you quotient by something of degree n, the elements of the quotient are given by the cosets of polynomials of degree less than the thing that you're quotienting by. So here I have to just take polynomials of degree up to 2. But the thing is that the coefficients come from f2, so the coefficients can only be 0 or 1. So there is only a finitely many polynomials of degree up to 2. What are they? There's 0, there's 1. So I'm just writing down the polynomials of degree 0, 1, and 2. There is x, there is 1 plus x, and there is x square, and there is 1 plus x square, and there is x plus x square, and then there is 1 plus x square. These are all the polynomials of degree up to 2. And if you take the cosets of them, that's your k. So this is k is a field with 8 elements. And let's play with this a little bit, but writing them like this as coset gets kind of irritating. It's better to, we have already promised that we are just gonna identify 0 plus f with 0 and 1 plus f with 1. And indeed, this is the 0 of this k, and this 1 plus f is the 1 of k. To name the other things, it's better to give a name to this guy. Let alpha be the coset of f. Then 1 plus x plus f is 1 plus alpha. X square plus f is alpha square. 1 plus x square plus the ideal, that's 1 plus alpha square. So once you do that, then you verify. Let's go up here. And verify that k is 0, but now by 0 I mean this 0, 0 plus f, which is the 0 of k. 1 alpha, 1 plus alpha, alpha square, 1 plus alpha square, alpha plus alpha square, and 1 plus alpha square. These are the 8 things in k. And the addition is very straightforward. I mean, if you add 1 plus alpha to 1 plus alpha square, you get 1 plus 1, 2, which is 0, alpha plus alpha, 2 alpha, which is also 0 because 2 is 0, so you just get alpha square, etc. So the addition is just the addition of f2. What about the multiplication? To know the multiplication, you have to realize, note that alpha cube plus alpha plus 1 is x cubed plus x plus 1, the coset of that. But then x cubed plus x plus 1 is your f. So this is just the ideal f, which is what we call 0 now. So x alpha cubed plus alpha plus 1 is 0 in k. Again, after you have identified this 1 and this 0 of f2 with the 0 and 1 of k. So you just need to remember this rule. This is sort of the master rule. Or even better, this is same as saying alpha cube is alpha plus 1. I really get minus alpha minus 1, but minus 1 and plus 1 are the same because we are over f2. So you just need to remember this rule, alpha cube equals alpha plus 1 to do the multiplication. So for example, so this determines multiplication in k. For example, let's take, I don't know, and together with the fact that 2 is 0. So let's do alpha square plus alpha plus 1 times alpha square plus 1. Just do this multiplication. What do you get? You get alpha to the 4 plus alpha to the 3 plus alpha 2, and then you get alpha square plus alpha plus 1. So that's alpha to the 4 plus alpha cube plus alpha plus 1. And then alpha to the 4 is alpha times alpha cube. And then alpha cube plus alpha plus 1 is 0. So this is just 0. Or let's be even more systematic. I'm just going to substitute whenever I see alpha cube by alpha plus 1. Let's not do it yet. And then for alpha cube, I'm just going to substitute alpha plus 1. And then if you simplify, you get alpha squared. And then you get, if I do it carefully, let's see, don't make a mistake. You get 2 1s, that goes away. This one and this one gives you 0. And you get alpha and alpha and alpha. So you get 3 alpha, which is alpha. Yeah. So which is again one of these 8 elements, you see. The point is that when you multiply, sometimes you'll get expressions which will have higher powers of alpha, but then you can use this master equation to bring down that power until everything is within degree 2. So that's why you always, everything looks expressions up to degree 2. So for example, this equation itself tells you alpha cube plus alpha is 1. Right? Alpha cube minus alpha is 1, but then alpha cube plus alpha is also 1, which means alpha times alpha square plus 1 is 1. That is, alpha square plus 1 inverse is alpha, and alpha inverse is alpha square plus 1. So you got some inverses. And then, for example, if you do, let's do another multiplication. Alpha square plus alpha plus 1 times alpha square. I think alpha square is the inverse of alpha square plus alpha plus 1. This gives you alpha to the 4 plus alpha cube plus alpha square. But alpha to the 4 again is alpha times alpha cube, which is alpha plus 1. And alpha cube is alpha plus 1 plus alpha square. So I just want to illustrate how this degree dropping works. And you see that is an alpha square here and alpha square here. That becomes 0. Then an alpha here and alpha here. That becomes 0. So this is just 1. So alpha square plus alpha plus 1 inverse is alpha square. And then you can finally also check, verify that k is 0, 1, alpha, alpha square, alpha cube, alpha to the 4, alpha to the 5, alpha to the 6, and alpha to the 7 is 1. Back to 1 again. So those are the 8 elements. And this is how a finite field typically looks like. So there's a general theorem here, which this indicates that for every prime p, there is a unique finite field of order p to the n, for any n. So this way, we can construct finite fields f p to the n for any prime p and any natural number n. And there is a fact that any finite field is one of these, meaning given any, so theorem for each prime number p and natural number n, there exists up to isomorphism a unique finite field fp to the n of order p to the n. And you just learned how to construct the one of order 8. And similarly, you can play with things and or construct the one of order 4, which will be even simpler. Just need to find a irreducible polynomial of degree 2 in f2x. You can construct one of size 9, one of size 25, one of size 27. So the small prime powers that you don't know yet. So this one will come from f5x. This one will come from f3x. This one also. So I indicated some of these in the exercises. Yeah, for the general construction, you have to know that there is a irreducible polynomial of any degree in fpx. And the structure of this finite field always looks like this. That's also part of the theorem. You can always find an element such that if you take all its powers up to the right place, you get the field. We'll stop.